Hey, what's up? Saturday morning, Friday night, March 26th, 2021. All right, that's today's date. And today I have another tree problem for you. Sorry about the noise outside. Somebody's apparently chopping wood at this hour or cutting trees or something like that. Doesn't matter. Yeah, I have another tree problem for you. I'll count Univalued subtrees. This is actually an interesting problem because, as you will see, um, and as I think, this problem is going to use our standard tree mechanics, but we're going to have to, it's a little more complex than simply traversing a tree, right? I mean, obviously that's going to be part of it, but we're also going to have to understand what the problem is asking us, okay? So the and what the statement of the problem is, given the root of a binary tree, return the number of univalued subtrees. Man, people are drag racing outside. So annoying. A univalued subtree means all the nodes of the subtree have the same value. Okay, so this is an example of a univalued subtree. If I have this guy here, if I have this entire tree, how many subtrees of this tree, right, have the same, have all their nodes having the same value. Okay, so this is an interesting problem because this is asking, first of all, for all the subtrees of any tree, right? And the question can look a little, to the unpracticed eye, can look a little deceiving, right? Because how many subtrees are there here? Well, there's this one tree, right? The tree is essentially a subtree of itself, but it is not univalued, right? Because it has a node that's 1. There's the next level of subtrees. There's this one subtree, so a second subtree, which is not univalued. Then the leaf nodes are actually subtrees, right? They're one node trees, so they are univalued. So any leaf node by default is going to be, um, a univalued tree. Okay, and then this subtree of 2 nodes is a univalued tree, and then its subtree is a univalued tree. Okay, they all have element 5. Okay, so this was actually a good example because, again, to the untrained eye, you would think that the whole tree would be univalued at first, but as you can see, this one invalidates the univaluedness of the entire tree, which is also a subtree of itself. So we need to find a way to do this. So the first thing that comes to mind, and the solution which I intend on coding up, is, well, we obviously have to traverse the tree, right? So we'll do a standard traversal, void DFS, tree node root, okay? And we're trying to count the number of univalued subtrees. So I want to maintain a counter, right? I'll call it counter. Okay. And in this function, I want to simply, if root equals null, right? So at that point, means that doesn't count. Null root does not count for anything. So we're just going to return. So I want to then now define my recursion condition, right? So if root, so now I'm going to have a function called univalued, right? Univalued is going to actually count the number of subtrees from the current tree that's univalued. Okay, so I'm essentially doing a nested DFS in here. Okay, a double DFS if you want to call it. And I will write out the details of this function in a minute, but if you can guess what this is going to do, this is going to somehow note whether the tree is univalued or not, right? Does this tree, all the nodes have the same value? If not, then obviously this will return a Boolean that says we are false. So in order to compare whether a tree has univalued nature, we have to compare it to something. So what I'm going to do from the beginning of the iteration for each subtree, I'm going to pass in the root, right? Because that's where we start. Wherever we start, that's the root of the subtree, including the root of the original tree. And then I'm going to just start compare it with itself, right? Now, when I get into the function, this might make more sense when I get into the function definition of univalued, right? So, and if it's true, if it does return a univalued tree, we'll have our reference counter making sure that that is accounted for. Okay, so then what we'll do is we'll go to the left, root.left, counter, and dfs root.right, counter. Okay, so that's where we're at. So now comes the, the core of the code. How do we define univalue? Okay, dfs, I'll call it univalue. So first, obviously, we have our root node wherever the subtree starts, and then I'm going to call a value. I'm going to call the second parameter passed down. Okay, so this is the value that I'm passing down through the tree to compare each root to determine whether the subtree below is univalued or not. Okay, so if root equals null, right? If there is no subtree, of course it's going to be univalued. The univalue is going to be null. So we're going to return true, and this is where the recursion would stop, right? Okay. Now, the details of this are more like, well, what do we have at this point? We want to determine whether the left and right subtrees are univalued, right? So that's, okay, we'll do that in a second, but let's see. If the core condition is if root.val not equal to passed down, right, then we're going to return false. Because if the current root is not equal to whatever we pass through the recursion, then the tree is not univalued. Okay, that's just the definition of a univalued tree. If it subtree, if its parents are univalued, right, and grandparents and all its ancestors and descendants, right? Like, all its descendants are univalued, then it's a univalued subtree. Okay, so that's 5, 5. The descendant 5 is univalued. So then finally, we want to univalued. So we want to make sure, in order to have a true univalued tree, we want to make sure that both the left and the right subtrees are univalued. Okay, root.right, passed down. Okay, so this is just pretty much ensuring that both branches of the subtree recursively are univalued. Okay, and then once it, the passed down value will have to always be the same value, right, that we originally passed down through the tree from the original iteration, right? And you can say, okay, do root.val, whatnot. It doesn't matter. This condition will have to hold true. Okay, throughout the entire recursion. So that should do it. And let's write the core of our helper function, our introduction method, our starting method, right? Main method, whatever you want to call it. So first we want to define our counter, and counter equals new int 1. This is just our little trick to create a reference counter that we can reference anywhere through the recursion, and we do this quite often in other problems. Then we do dfs root and root.val, because what we want to do is, as an initial condition, we compare. It's going to obviously be true. Any root is going to be a univalued tree. It's going to be part of a univalued tree if it's the only node there. So that'll cover that condition. And then we return counter of 0. So we return the first value of this referenced element here. So let's try running this. Compiler error, of course. What cannot be converted to what? Root.val. We want to pass counter. This is, sorry. Yeah, okay. This should be right. Sorry, I had my logic a little incorrect. We want to pass the counter that we just created through the recursion. And that was accepted. Okay. I'm going to submit to run it against all the test cases, not just the one. And voila, the whole problem was accepted. And it's faster than 100% of other Java submissions, right? So that's doing really well. The space constraint, 66.26%. And I think really the reason for that is the double DFS, because we're maintaining two sets of stack frames. If we iterated through this tree, I think the recursion stack space wouldn't accumulate, and therefore we would have maybe close to 100% memory that we're faster than, instead of being in the 66th percentile. Okay, and yeah, so that's the problem. If you think this video was helpful, like, subscribe, leave messages in the comments below, and doing all that helps me make more videos. And if you found this useful, let me know. If you want me to change anything, let me know. I'm glad to hear all feedback. And I hope your programming, your coding, your interviews, and your computer science knowledge increase, and everything goes well for you. All right. Have a good night.